The Lyncole XIT system is recognized for its reliability and ease of installation. It is a proprietary system that combines a straight shaft with Western bentonite backfill. Western bentonite is a high-quality material that expands when hydrated, creating a watertight seal around the grout hole. The system has been successfully used in a variety of soil conditions, including shallow rock. There are several other comparable systems on the market. Firstly, Ram Jack Pile Systems offers a range of deep foundation systems, including screw piles and helical piles. Secondly, Helical Piers of America provides helical piers that can be installed in a variety of soil conditions, including shallow rock. Thirdly, Earth Contact Products, or ECP, manufactures a wide range of foundation solutions, including helical piers and driven piles. Fourthly, Spartan Helical specializes in helical piles for both residential and commercial applications. When choosing a foundation system for shallow rock, consider several factors. 1. Soil conditions. The type and depth of the rock will influence the appropriate system. 2. Load requirements. The weight of the building will determine the size and capacity of the system required. 3. Installation accessibility. The location of the building and surrounding structures may affect the ease of installation. 4. Cost. Compare the costs of different systems, including materials, labor, and permits. Based on the description provided, the Lyncole XIT system appears to be a suitable option for the building site. However, it is recommended to consult with a qualified foundation engineer to determine the best system for the specific needs. They can evaluate the soil conditions, load requirements, and installation feasibility to provide an optimal solution. Understanding soil composition is important. Soil is composed of mineral particles, organic matter, water, and air. The proportions of these components vary depending on the soil type and location. Soil texture refers to the size distribution of mineral particles in the soil. The three main size fractions are sand, silt, and clay. Sand particles are the largest, ranging from 0.5 to 2 mm in diameter. Silt particles are smaller, ranging from 0.2 to 0.5 mm. Clay particles are the smallest, less than 0.2 mm. Soil structure refers to the arrangement of soil particles into aggregates or clumps. Soil structure affects water infiltration, aeration, and root growth. Soil classification systems are used to group soils with similar properties and behaviors. The most common soil classification system in the United States is the USDA soil taxonomy. Soil testing is an important part of foundation design. Soil tests can provide information about the soil's properties, such as its bearing capacity, shear strength, and permeability. Bearing capacity is the ability of the soil to support the weight of a structure. Shear strength is the soil's resistance to sliding or deformation. Permeability is the rate at which water flows through the soil. Foundation design involves selecting the appropriate type of foundation for a particular site and structure. The type of foundation chosen will depend on the soil conditions, load requirements, and other factors. Shallow foundations are typically used when the soil has sufficient bearing capacity to support the structure's weight. Deep foundations are used when the soil is weak or unstable. Spread footings are a type of shallow foundation that distributes the load over a wide area. Mat foundations are another type of shallow foundation that is used when the soil is very weak. Pile foundations are a type of deep foundation that uses long, slender columns to transfer the load to deeper, more stable soil layers. Drill shafts are another type of deep foundation that is similar to pile foundations but are installed by drilling a hole and filling it with concrete. Helical piers are a type of deep foundation that uses screw-like steel shafts to transfer the load to deeper soil layers. Ground improvement techniques can be used to improve the soil's properties before foundation construction. Compaction is a technique that increases the density of the soil, making it stronger. Soil stabilization is a technique that uses additives to improve the soil's properties, such as its bearing capacity or shear strength. Geotechnical engineering is a branch of civil engineering that deals with the behavior of soil and rock. Geotechnical engineers are involved in all aspects of foundation design and construction. Site investigation is an important part of geotechnical engineering. Site investigations involve collecting information about the soil and rock conditions at a particular site. This information is used to design the foundation and other geotechnical structures. Slope stability analysis is another important part of geotechnical engineering. Slope stability analysis is used to determine the stability of slopes, such as those found in embankments or hillsides. Retaining walls are structures that are used to support soil or rock slopes. Retaining walls are commonly used in construction to create level areas or to prevent erosion. Earth dams are large structures that are used to store water. Earth dams are typically constructed from compacted soil and rock. The design and construction of earth dams requires careful consideration of the soil and rock conditions. Construction geotering is the process of removing water from a construction site. Construction geotering is often necessary to allow for excavation and foundation construction. Erosion control is the process of preventing soil erosion. Erosion control is important in construction to protect the environment and to prevent damage to property. The National Electrical Code, or NEC, provides guidelines for grounding and bonding electrical systems. Grounding is the process of connecting electrical equipment to the earth. Bonding is the process of connecting different metal parts of an electrical system together. The purpose of grounding and bonding is to provide a safe path for fault current to flow back to the source, which helps to protect people from electric shock and to prevent damage to equipment. Article 250.4 of the NEC covers general requirements for grounding and bonding. Article 250.50 covers grounding electrode systems. Article 250.52 covers grounding electrodes. Article 250.64 covers grounding electrode conductor connections. Article 250.66 covers size of grounding electrode conductor. Article 250.102 covers bonding jumpers. Article 250.104 covers bonding of metal water piping systems and other metal work. Ground rods are a common type of grounding electrode. Ground rods are typically made of copper or copper-clad steel and are driven into the ground. The NEC requires that ground rods be at least 8 feet long and 1/2 inch in diameter. Ground rings are another type of grounding electrode. Ground rings are typically made of bare copper wire and are buried in a trench around the perimeter of a building. Concrete encased electrodes, also known as U-for-grounds, are another type of grounding electrode. Concrete encased electrodes are made by encasing a bare copper conductor in concrete. Metal water pipes can also be used as grounding electrodes, but they must meet certain requirements. The metal water pipe must be in direct contact with the earth for at least 10 feet. The metal water pipe must also be electrically continuous. Structural metal can also be used as a grounding electrode, but it must meet certain requirements. The structural metal must be electrically connected to the earth. The structural metal must also be of sufficient size to carry the fault current. Lightning protection systems are designed to protect buildings from lightning strikes. Lightning protection systems typically consist of air terminals, conductors, and grounding electrodes. Air terminals are installed on the roof of a building to intercept lightning strikes. Conductors are used to carry the lightning current from the air terminals to the grounding electrodes. Grounding electrodes are used to dissipate the lightning current into the earth. The selection of a grounding system depends on several factors, including the soil conditions, the size of the building, and the type of electrical system. In areas with high soil resistivity, it may be necessary to use multiple grounding electrodes or to install a ground-enhancing compound. The installation of grounding systems should be performed by a qualified electrician. Grounding systems should be inspected regularly to ensure that they are in good condition. Improper grounding can be dangerous and can lead to electric shock or equipment damage. The information provided here is for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified engineer or electrician before making any decisions about grounding or foundation design. When evaluating different foundation systems, consider the long-term performance and maintenance requirements. Some systems may require periodic inspections or maintenance to ensure their continued effectiveness. Consider the environmental impact of the foundation system. Some systems may have a smaller environmental footprint than others. For example, helical piers can often be installed with minimal disturbance to the surrounding soil. Research the track record of different foundation system manufacturers. Look for companies with a proven history of providing reliable and effective solutions. Get multiple quotes from different contractors before making a decision. This will help ensure that you are getting a fair price for the work. Check the contractor's references and make sure they are properly licensed and insured. A thorough understanding of soil mechanics, foundation design principles, and electrical grounding practices is essential for ensuring the safety and stability of any structure. Remember to prioritize safety and consult with qualified professionals throughout the design and construction process.